Hello students, welcome back to the sixth video of this playlist. In this video, we will be solving question number 6 from the most recent past paper of Mechanics 2, which is the October 2024 M2 paper. So let's get started with question number 6 of this paper. Okay, so here the fifth figure of this paper, figure number 5. So the question number 6, it says a uniform beam AB of weight 5W and length 12A rests with end A on rough horizontal ground. A package of weight W is attached to the beam at point B. Where is point B? Okay, to the right end of the beam. Okay, the beam rests in equilibrium on a smooth horizontal peg at the point C with AC equals to 9A as shown in figure 5. Okay, the beam is inclined at an angle theta to the ground where tan theta equals to 5/12. Okay, so the beam is modeled as a rod that lies in a vertical plane perpendicular to the peg. The package is modeled as a particle. The normal reaction between the beam and the peg at C has magnitude K times W. Okay, so so the package that has been placed at point B, it is considered as a particle. That means its weight is acting from a single point. And the beam is modeled as a rod. That means it is what you can say, it has no thickness. We can ignore the thickness of the rod, and it is rigid. A rod is basically rigid. Okay, these are the modeling assumptions. Fine. So using the model, part A is asking to show that the value for K, it is 56/13. Okay, so we need to find out the value for K. What is K? K is basically the normal reaction between the peg and the beam. Okay, so let me show the forces that is acting. At first, the normal reaction from the peg on the beam, it is acting vertically, that is perpendicularly in this direction, right? So this is KW, and the beam is uniform, so that means the weight of the beam, it is acting from the right at the middle, right? So this is the weight of the beam, which is 5W. Okay, and since the beam is attached to the ground at the point A, so definitely at point A there will be perpendicular normal contact force acting, right? So this is the normal reaction at the point A, and we know that there is a package of weight W Newton. Yeah, package of weight W, it has been placed at the point B. So this is the weight of the package W. Okay, and the friction. So we don't know exactly the direction of friction. The direction of friction can be either this way or that way. But since there are no forces acting on the beam along that way, so we can say that the beam is trying to move or trying to slide on the left direction. Therefore, friction is acting on this way. Okay, now let's have a look. So to find the value of K, we don't know the normal contact force at A. We don't know the magnitude of friction. So definitely we have to ignore these forces. So in this case, we will consider moments about the point A. So if you consider moments about point A, then the perpendicular distance of RA and the perpendicular distance of the friction will be 0, and therefore their moments can be ignored. So let's take moments about the point A. Okay, so taking moments about A, we are taking moments about A. So clockwise moments are the weight of the beam, that is 5W, and its perpendicular distance from the point A, it is basically halfway of the length of the beam. So total length of the beam is 12A, so halfway is basically 6A. Okay, so this is the moment, clockwise moment due to the weight of the beam. And another clockwise moment is the, okay, we have to consider the perpendicular distance, not the direct distance. So we have to consider this distance. Okay, direct distance is, this is fine, 6A. Okay, but the perpendicular distance, it is not 6a. You should be careful on that. I have done a mistake there. It should be 6a cos theta. Okay, why 6a cos theta? Consider, we need this distance. This is the perpendicular distance. Moment is equals to fx, where x is the perpendicular distance between the line of action of the force from the pivot. Okay, so the perpendicular distance, it is basically this distance, 90°, making 90° with the line of action of force. So to get this distance, we have to consider cos theta. Okay, so cos theta, look there, cos theta equals to the perpendicular distance is the adjacent side x over the hypotenuse. Hypotenuse is 6a. So x equals to 6a cos theta. 6a cos theta. That's what I wrote here. Okay? Plus the clockwise moment, it is provided by the another clockwise moment, it is provided by the weight of the package, that is W. So W times it would be W times same perpendicular distance would be now 12a cos theta, because the direct distance from the point A to the package B, package at point B, it is basically 12a. So its perpendicular distance would be 12a cos theta. This is the clockwise moment. And the anti-clockwise moment, it is only due to the normal contact force at the point C, which is Kw times, now what would be the perpendicular distance? We can see that the normal contact force at C, it is making 90° with the beam. So the direct distance is the perpendicular distance. So it is 9a. So Kw times 9a. Okay, it is 9a. Okay, now calculate the values. W cancels from both sides. So 6 times 5, it is basically 30. A also get cancelled out. A there, A there, A there. They cancels out. So 30 times cos theta. The value for cos theta, it is, okay, tan theta is given as 5 over 12. Okay. Tan theta equals to 5 over 12. Therefore, cos theta, tan theta is opposite side over the adjacent. Cos theta is adjacent over the hypotenuse. So adjacent is 12. So cos theta is 12 over 13. Okay. So 30 times 12 over 13. Okay. W cancels out from both sides. A cancels out from both sides. So this is 30 times 12 over 13 plus W gets cancelled there. A get cancelled there. So W times cos theta. Cos theta is again 12 over 13. This is 12 over 13. Okay. This is equals to 9 times K. Right. The AW has been cancelled. So now we need the value for K. Now just use your calculator to get the value for K. So 30 times 12 over 13 plus 12 times 12 over 13, okay, divided by 9. So that would give you 56 over 13. Okay, we got the value for K. And is it the value for K as per the question? 56 over 13, exactly. That's the answer for part A. Fine. Okay, next is part B. In part B, the question says the coefficient of friction between A and the ground is mu. Okay, given that the beam is resting in limiting equilibrium, so part B is asking to find the value of the coefficient of friction, that is mu. Okay, so the beam is resting in equilibrium. So we could see that the friction is acting in this direction. So how do we figure out the direction of friction? Because since there are no forces acting to the right direction, okay, so definitely the beam will tend to move on the left direction. Therefore the friction will act on the opposite direction, that is to the right. Okay, so to get the value for the mu, okay, to get the value for mu, how can we do the work to get the value for mu? Look, at first consider the forces. Okay, before considering the forces, at first try to think of one fact here. We know that in limiting equilibrium, friction is maximum, right? And maximum friction Fmax is equals to mu times R. So here the normal contact force is at A, so mu times RA. So definitely we have to know the normal contact force at A. To figure out that normal contact force at A, we have to consider the forces vertically. Okay, we have to consider the forces acting on the beam vertically. Okay, for part B, consider the forces acting on the beam vertically. Okay, so what are the forces acting vertically? The reaction at A is acting vertically upward. And what is acting vertically upward? The component of the normal contact force at C. Look, this component, this is perpendicularly upward. Okay, this component we need to figure out. This is the perpendicular component of the normal contact force at C. So this angle is basically theta. Okay, this angle is theta. So we need the vertical component. So vertical component can be found using cos theta, right? Okay, how cos theta? Look, cos theta equals to adjacent side. Adjacent side is basically the perpendicular component of the normal contact force at C. So RV over the normal contact force at C. So RV, it is equal to the vertical component of the normal contact force at C. It is RC cos theta. RC cos theta. These are the perpendicular forces upward, equals to, since the system is in equilibrium, it is equals to the downward forces. What are the downward forces here? The weight of the beam, that is 5W, and the weight of the package at B. So 5W plus W. Okay, now get the value for reaction at A. So RA, it is equals to 6W minus reaction at C, it is KW. K is 56/13 that we found just in part A. 56/13 W. Cos theta. Cos theta is 12/13. Okay, is this the cos theta we got in part A? This is 12/13. This is cos theta. Fine. Now get the value for RA using the calculator. So reaction at A, it is equals to 56/13 times 12/13. So we have to subtract it from 6. So this is basically 342/169 W. That's the reaction at A. Okay. Okay, now we got the reaction at A. Now we have to consider the friction, right? Fmax equals to mu R. We got the value for reaction at A. Now we have to consider the forces horizontally to consider the friction, right? Because friction is acting horizontally, friction has gotten no component along the vertical direction. So we have to consider the forces horizontally acting on the beam. Okay, now consider the forces acting horizontally. So horizontally, friction, it is acting to the right side. Okay, this is the friction F. F is equals to what is acting to the left? Yes, the horizontal component. Look, the horizontal component of the reaction at C, it is acting to the left. So F equals to the horizontal component of the reaction at C. This has to be found using sine theta. So sine theta equals to horizontal component of the reaction at C over reaction at C, opposite over the hypotenuse. So horizontal component is F equals to RC sine theta. Okay, are there any other forces acting horizontally? Nothing else. Nothing else. Okay, now consider the friction is maximum. So we can write friction is mu times reaction at A equals to reaction at C, it is 56/13 W sine theta. Okay, so tan theta, it is equals to 12/5, if I'm not wrong. 12/5. It is 5/12. Okay, it is 5/12. The opposite way, 5/12. Therefore sin theta, tan theta is opposite side over the adjacent side. So sin theta would be opposite. Opposite is 5, and hypotenuse is 13. So 56/13W times 5/13. Okay. So we got the reaction at A. It is 342/169 W times mu. It is equals to 56/13 times 5/13. That would give you 280/169 W. So W cancels out from both sides, and then multiply both sides by 169. So you will get 342 mu. This is equals to 280. Okay. So the value for mu, it is 280/342. 280/342. That is basically 140/171. Okay. 140/171. That's the exact value for the coefficient of friction between the ground and the beam at the point A. That is 140/171. And that's the answer for part B of question number 6. Fine.